You are about to meet one star that makes our sun look small and contained, a red supergiant so expanded it could swallow most of the solar system. It sits in a quiet patch of sky in the constellation Scutum, roughly 6,000 parsecs away, about 20,000 light-years. Astronomers call it Stephenson 218, a massive late-stage star, already off the main sequence and swollen into a huge, cool, unstable envelope of gas. But before we continue, please subscribe to the channel to give your support. Let's continue. We are talking about one star, not a cluster or a background galaxy. The reason it keeps appearing in largest star discussions is simple. When you rank stars by radius, Stephenson 218 is at or near the top. So here are the numbers. Current estimates give Stephenson 218 a radius of about 2,150 times the Sun's radius. The Sun's radius is around 700,000 kilometers, about 430,000 miles. Multiply that by more than 2,000 and you get a radius of roughly 1.5 billion kilometers, close to 930 million miles. Double that for the diameter and you get about 3 billion kilometers across, around 1.9 billion miles. These values are not exact. They come with large uncertainties because we infer them from light, not from direct size measurements. The studies that quote a radius near 2,150 solar radii usually add a warning. The distance and other inputs may be off by a lot. Now, the surface temperature. You might expect a star this big to be extremely hot on the outside, but it is cooler than the sun. The photosphere of Stephenson 218 is around 3,200 Kelvin, roughly 3,000 degrees Celsius, about 5 to 6,000 degrees Fahrenheit. The sun's visible surface is closer to 5,800 Kelvin, so our much smaller star actually has the hotter surface. That lower temperature is why Stephenson 218 glows deep red instead of yellow-white. So you have a cooler surface than the sun, but a radius thousands of times larger. The total power output is still enormous because there's such a huge area radiating energy. That leads to the key question. If you put this star where the sun is now, what would it do to the structure of the solar system? Inside a planetary system, astronomers use the astronomical unit. One astronomical unit is the average distance from Earth to the sun, about 150 million kilometers. Earth is at 1 astronomical unit, Jupiter at about 5.2, Saturn at about 9.5 astronomical units. A radius of about 2,150 solar radii works out to roughly 10 astronomical units. So if you replace the sun with Stephenson 218 and leave the planets where they are, the surface of the star reaches somewhere between Jupiter's orbit and Saturn's orbit, and its outer layers practically touch Saturn's path. All the inner planets and the asteroid belt are deep inside the star's envelope. Jupiter orbits inside that extended atmosphere, and Saturn moves through its thin outer regions. From the standpoint of planets, the inner solar system stops being a set of exposed worlds and becomes a group of objects buried inside a star. That is the scale we are dealing with, and it forces you to adjust how you think about what a star is. A normal star is a compact ball of plasma, dense in the middle, clearly separated from the vacuum around it. Stephenson 218 does not fit that picture. If you take a radius more than 2,000 times larger than the sun's and cube that factor, you get a volume around 10 billion times the sun's volume. You are spreading something like a few tens of solar masses over 10 billion solar volumes. When you do that, the average density becomes extremely low, thousands of times lower than the air you are breathing right now. The gas at the level we call the surface is extremely thin, but still at thousands of degrees and bright enough to radiate. Stephenson 218 is basically an enormous, weakly held shell of hot gas, stretched close to the limit of what gravity can keep together. Now, the obvious challenge. Are we sure it's really that big, or are the measurements misleading us? This is where the largest star controversy starts. That famous radius depends heavily on how far away Stephenson 218 is, and that distance is not perfectly known. Many analyses place it in or near a massive cluster of red supergiants called Stephenson 2, but that region is dusty, and the standard distance methods can be wrong by tens of %. A star's true luminosity scales with the square of the distance. distance. So if the distance is off by 50%, the luminosity is off by more than a factor of 2. For a fixed temperature, the derived radius then shifts by about the square root of that change. Some researchers also argue that Stephenson 218 may not actually belong to the Stephenson 2 cluster, and might sit closer to us as a foreground object. In that case, the real radius and luminosity would be smaller. Other work says the star's motion and properties line up well enough with the cluster that it's likely a true member, which keeps the extreme numbers in play. The honest summary is simple. Stephenson 218 is clearly an extreme red supergiant or hypergiant, but the precise radius is still being argued over. For you, the key point is that even if you shrink it, even if later measurements bring it down to, for example, 1500 solar radii, or even closer to 1000, it still easily engulfs the orbits of the inner planets and probably Jupiter as well. So yes, we might be overestimating this object, but even the scaled-down version is still a star that wrecks the normal idea of how large a star can be. So the basic picture is in place. A red supergiant or hypergiant around 20,000 light-years away in the direction of Scutum, with a radius on the order of 10 astronomical units and a volume roughly 10 billion times larger than the Sun's. The next question pushes the tension up another step. Where exactly in the Milky Way does a star like this live? What kind of cluster and spiral arm environment allows something this big to form and survive even for a short time? How does a star this big end up in such a specific part of the galaxy? And what does its neighborhood tell you about how extreme it really is? Stephenson 218 doesn't live alone in some quiet corner. It hangs right next to a huge crowded group of massive stars called Stephenson 2, also called RSGC2, short for Red Supergiant Cluster 2. This cluster is loaded with red supergiants, not one or two, but dozens, each of them already among the largest stars ever seen. You are looking at a region that has produced a whole batch of massive stars, all born roughly at the same time, all evolving off the main sequence together. The distance estimates for this cluster sit around 5.5 to 6 kiloparsecs. That's about 18 to 20,000 light-years. When you point an infrared telescope into that direction, you don't see one lonely giant. You see a whole collection of swollen, dying stars packed into a relatively small volume of space, and Stephenson 218 is one of the most extreme members of that group, if it really belongs to it. So the first piece of the picture is this. Stephenson 218 is not some weird one-off in isolation. It sits in or near a factory that specializes in creating high-mass stars that end their lives as red supergiants. That cluster tells you the environment is young on cosmic timescales, maybe a few tens of millions of years old, and that it formed from a very dense, rich cloud of gas, the kind of place where you expect to see heavyweights that will go supernova. That raises the next step. What kind of larger galactic structure builds a cluster like this in the first place? Where in the Milky Way do you park that many massive stars? Stephenson 2 and Stephenson 218 lie in the direction of the Scutum Centaurus arm, one of the major arms of the Milky Way. Spiral arms aren't just pretty patterns, they're regions where gas and dust are compressed, star formation gets boosted, and big clusters form. The Scutum Centaurus arm is especially active, full of giant molecular clouds, H2 regions, and young massive clusters like this one. You can think of that spiral arm as one of the galaxy's high production zones for big stars. The Sun sits in a quieter neighborhood, a smaller structure called the Orion arm or Orion spur, but Stephenson 2 is sitting right in a heavy industrial zone for star formation. That matters because to get a star that starts out with 30 to 50 times the Sun's mass, you need a place with a lot of raw material and strong triggers for collapse. This arm supplies both. Dense gas, strong shocks, and gravity working overtime. Now, you might say, if this cluster and this spiral arm are such clear features, why is the distance to Stephenson 218 still such a mess? Why can't we just measure it cleanly and settle the argument? At first glance, distance sounds easy. You just measure parallax, the tiny apparent shift in a star's position as Earth moves around the Sun. That works well for nearby stars, where the angle is large enough for instruments like Gaia to detect accurately. But at around 20,000 light-years, the parallax angle becomes incredibly small, far below 1,000th of an arcsecond. And on top of that, this region is packed with dust and other stars. The dust dims the light, the crowding confuses measurements, and the parallax solution becomes noisy or unreliable. So astronomers fall back on indirect methods. They measure the radial velocity, basically how fast a star or cluster is moving toward or away from us, then plug that into models of how the Milky Way's disk rotates. Those rotation models translate a given line-of-sight velocity into a rough distance. The problem is, those models are not perfect. The galaxy's rotation is not a simple, clean curve, and along some directions there are near-far distance ambiguities. On top of that, the dust can change the brightness in ways that are hard to correct. All of this piles up into distance estimates that can be wrong by tens of percent. That is how you end up with phrases like distance uncertain by more than 50%. If distance is that shaky, then everything that depends on distance, like luminosity and radius, becomes shaky too. And that is exactly the source of the largest star debate. So we have a dusty line of sight, crowded star field, and suspiciously big error bars, which leads to a different question. How do you even study something that faint and obscured in the first place? What do you actually look at when visible light is mostly blocked? Along this sightline, interstellar dust is brutal to visible light. It absorbs and scatters shorter wavelengths, so in regular optical images, the region looks dim and messy. But dust is much more transparent in the near-infrared. That is why surveys like 2MASS and similar infrared sky maps were crucial. They could see through much of the dust and pick out unusually bright red objects that turned out to be red supergiants. Stephenson 2 and its members, including Stephenson 2-18, stand out in those infrared colors. They look very bright at longer wavelengths where the dust has less impact. Once the cluster was identified in infrared catalogs, astronomers followed up with more targeted observations, still mostly in infrared, to measure brightness in several bands, estimate how much extinction the dust is causing, and then derive rough temperatures and luminosities. So, in a real sense, the galaxy was hiding these massive stars behind thick dust lanes, and they only became obvious when we switched to the right part of the spectrum. That's why even though this is a huge cluster with multiple red supergiants, it was only recognized relatively recently, and why its distances and properties are still being tuned. But there is one more problem that keeps this story unsettled, and it goes straight to the heart of how extreme Stephenson 2-18 really is. Can we be sure it actually belongs to Stephenson 2 at all? Some studies treat Stephenson 2-18 as a clear member of the cluster. Its position on the sky, its color, brightness, and approximate velocity all look consistent with the rest of the group. If that is correct, then its distance is basically the cluster distance, around 5.5 to 6 kiloparsecs. And that is what gives you the enormous luminosity and radius, hundreds of thousands of times the sun's power output, and the size on the order of 10 astronomical units. In that case, it really is one of the most luminous and extended red supergiants ever found. Other work, though, points out that the uncertainties in its motion and the depth of the region leave room for a different option, that Stephenson 2-18 might be a foreground interloper. In plain language, that means it could be closer to us than the main body of the cluster, just lined up in the same direction by chance. If that is true, the distance drops, the intrinsic brightness drops, and the radius shrinks. It would still be a large red supergiant, but maybe not the absolute top of the chart. So you end up with this tension. If Stephenson 2-18 is really a cluster member, it pushes right up against or beyond the limits of what our models say is possible for a red supergiant. If it is closer and smaller, our theories are safer, but we lose one of the cleanest examples of an ultra-extreme star. Either way, even the down-rated version is still absurdly huge compared to normal stars, still something that engulfs interplanetary orbits with ease. And that sets up the next deeper question you need to confront. Once you accept that this star is either extremely large or still very large, how do you actually build it from a normal massive star? What does the life story of a star have to look like for it to reach the point where its atmosphere stretches over billions of kilometers? Stars this big do not start out swollen, so the first thing you need to know is how a normal, compact, massive star turns into something that can reach across planetary orbits. Stephenson 2-18 probably began life as a very hot, very bright blue O-type star, burning hydrogen in its core at an extreme rate. With an initial mass somewhere around 30 to 50 times the Sun's mass, it would have rushed through its early life. While the Sun will spend about 10 billion years on the main sequence, Stephenson 2-18 would have left that phase after just a few million years. In other words, by the time a Sun-like star has barely started its story, a star like Stephenson 2-18 has already burned through its core hydrogen and is moving into its late, unstable stages. You can think of its early life as a high-power, short-duration mode. The core is so hot and dense that hydrogen fusion runs at a furious pace. The star shines hundreds of thousands of times brighter than the Sun, and the outer layers are held tight only because gravity is so strong. But that balance doesn't last. As the core hydrogen runs out, the star can no longer support itself in the same way, and the whole structure has to readjust. That readjustment is what pushes it off the main sequence and starts the path toward the red supergiant phase. So, what do the starting conditions have to look like to even have a shot at becoming a monster like this? Most red supergiants come from stars in the 8 to 25 solar mass range. Those stars already dwarf the Sun and end their lives as core collapse supernovae. But the really extreme cases, the ones that may reach Stephenson 2-18 scale, likely start higher, around 30 to 50 solar masses. At those masses, gravity in the core is intense, pressures and temperatures jump up, and the luminosity can reach into the hundreds of thousands of solar luminosities. That much power from one object means the star is constantly pushing its own envelope outward. Radiation pressure is strong, convection is violent, and the star is already losing mass through stellar winds before it becomes a red supergiant. If you wanted rough numbers, a 30 to 50 solar mass star might pump out something like 400,000 to 600,000 times the power of the Sun, while weighing only a few dozen times more. Mass gives it gravity, but luminosity gives it a huge outward push. It's a built-in conflict. Once such a star leaves the main sequence, the internal structure changes in a very specific way. Hydrogen fusion in the core shuts down because the core hydrogen is used up. But the core does not just sit still. It contracts, heats up, and begins to fuse helium into heavier elements like carbon and oxygen. Hydrogen fusion does not disappear. It moves into a shell around that helium-burning core. As the evolution continues, new shells can ignite. You can end up with hydrogen fusing in an outer shell, helium fusing in a shell beneath that, and eventually, deeper inside, shells where carbon, neon, oxygen, and later silicon burn for shorter and shorter times. Each shell adds energy to the total output. So instead of a simple one core, one fusion zone configuration, you have a layered structure that dumps huge amounts of energy into the overlying envelope. The key detail is that the outer layers of a red supergiant like Stephenson 2.18 are very low density and not strongly bound. When all those fusion shells pump more energy out, the envelope does not respond mainly by heating up and staying compact. It responds by expanding. The gas can move outward, gravity struggles to pull it back, and the star's radius grows while the surface temperature actually drops. That leads straight to the big question. Why does a star like this end up so large and so cool at the same time? There's a basic relationship that connects luminosity, radius, and surface temperature. In words, the total power output of a star equals a constant times its surface area times its temperature to the fourth power. Surface area grows with the square of the radius, temperature enters to the fourth power. So if you know roughly how bright the star is compared to the sun, and you know its surface temperature, you can back out the radius. For Stephenson 2.18, the estimates you hear, radius around 2,150 times the sun and temperature around 3,200 Kelvin, naturally give you a luminosity of a few 100,000 suns. Flip that around, if you assume a luminosity in the range of 400,000 to 600,000 times the sun, and you insist on a cool surface of about 3,200 Kelvin, the only way to satisfy that relation is to spread the energy over a huge area, which means a huge radius. In metric terms, you end up with that radius of about 1.5 billion kilometers. In imperial terms, that's about 930 million miles. The star is effectively choosing to radiate an enormous total power through a very large, relatively cool surface, instead of a smaller, hotter one. That is why it shows up as a deep red, extended object, rather than a compact blue-white point. But to really feel how extreme that is, it helps to compare Stephenson 2.18 to a red supergiant you've probably heard of already, Betelgeuse. Betelgeuse up in Orion is itself a huge red supergiant. Its radius is around 640 to 760 times the sun's radius. Put it in place of the sun and Betelgeuse would engulf Mercury, Venus, Earth, and Mars, and reach past the orbit of Mars toward the asteroid belt, but it likely would not reach Jupiter. That's already shocking for most people when they first hear it. Stephenson 2.18, even with conservative estimates, goes far beyond that. If you take the typical radius values quoted, it's more than 3 times larger in radius than Betelgeuse. Radius times 3 means volume goes up by roughly a factor of 20 to 30. So you're looking at a star with tens of times the volume of Betelgeuse, not just a small step up. Even if you downscale Stephenson 2.18's radius a bit because of distance uncertainties, it still stays significantly larger than Betelgeuse. Then you have other extreme red supergiants and hypergiants in the mix, names like VY Canis Majoris and UY Scuti. For a while, UY Scuti was often quoted as the largest known star, with radius estimates well over 1,000 solar radii. Later work revised its distance and shrank its estimated size. VY Canis Majoris has also gone through similar revisions. Stephenson 2.18 enters that same group, competing for the top spot. Which one sits at number 1 depends on which set of distances and models you accept at any given time. So the life story so far is this. Start with a star dozens of times heavier than the sun, run through hydrogen in the core in just a few million years, set up multiple fusion shells that dump massive amounts of energy into a light extended envelope, and the result is a red supergiant with a luminosity of several 100,000 suns and a radius that can reach roughly 10 astronomical units. That brings up the next crucial issue, which is also the source of a lot of the controversy and tension around Stephenson 2.18. How do we actually get those numbers from Earth? How do we go from a faint, dust-obscured point of light in the sky to a claim that its radius is bigger than planetary orbits? And how fragile are those claims to small errors in distance and temperature? How do you go from a faint red point buried in dust to the claim that this thing is billions of kilometers across? From Earth, you never see a disk for Stephenson 2.18. You only see light. So astronomers have to back out the radius using the chain of indirect steps. First, you measure how bright the star looks in different filters, especially in the infrared where dust hurts you less. That gives you an apparent brightness, how much energy per square meter hits your telescope here. Then you estimate how much of that light was stripped away by dust between us and the star. That correction is called extinction. After that, if you know the distance, you can work out the true power output, the luminosity, basically how many watts the star is really emitting. Once you have luminosity, you still need surface temperature. That comes from the spectrum and from color indices, the relative brightness in different bands. For Stephenson 2.18, its spectrum is that of a very cool late-type red supergiant, around class M6. That puts the effective temperature near 3,200 Kelvin. With temperature and luminosity in hand, you finally use the standard relation that links them to radius. Total power equals a constant times surface area times temperature to the 4th power. You solve that for radius. There is no physical measuring stick going out to 20,000 light years. It's all done by combining distance, brightness, and temperature in this way. So where does that whole chain start to wobble? The fragile part is the distance, because distance feeds straight into luminosity. If you hold the apparent brightness fixed and you move the star farther away, the true luminosity has to go up with the square of the distance. Double the distance and the luminosity goes up by a factor of 4. Cut the distance in half and luminosity drops to 1/4. For something like Stephenson 2-18, where we are talking about distances of roughly 18 to 20,000 light years with big uncertainties, that matters a lot. Say the real distance is 50% smaller than you thought. That is not a small tweak. That is a distance correction from around 20,000 light years down to maybe 13,000. Because luminosity scales with distance squared, the true luminosity would then be a bit more than 2 times smaller than you originally calculated. And radius for a fixed temperature scales roughly with the square root of luminosity. So if luminosity drops by a factor of a bit more than 2, radius drops by about the square root of that, roughly 40%. That is how you go from about 2,150 solar radii to maybe closer to 1,300 solar radii in one step, without changing any of the temperature assumptions. This is why astronomers constantly say that Stephenson 2-18 size is heavily distance dependent. But even if you pin down distance perfectly, you still have to ask, how sure are we about that surface temperature? Because the temperature enters in a way that amplifies errors. The star's spectrum around M6 and its infrared colors point to an effective temperature near 3,200 Kelvin. That is low compared to the sun's 5,800 Kelvin, but normal for a very cool red supergiant. The trouble is that modeling the atmospheres of such stars is messy. You have molecules, dust, and complex convection affecting the spectrum. If your temperature estimate is off by even a few hundred Kelvin, the radius you compute shifts. Remember, in that relation, luminosity is proportional to radius squared times temperature to the 4th power. If you underestimate the temperature, you will overestimate the radius to get the same luminosity. If you overestimate the temperature, you will underestimate the radius. For a star this cool, changing the assumed temperature from, say, 3,200 Kelvin to 3,500 Kelvin is less than a 10% change in temperature, but because temperature acts to the 4th power in the luminosity formula, that change has a much bigger effect on radius when you solve it backwards. Then you pile on the dust problem. Extinction corrections are not exact. You have to assume a certain dust law along that line of sight, basically how much each wavelength is dimmed. If that law is off, you misestimate how much light was lost on the way to us, and your luminosity goes wrong again. You also have to assume a bolometric correction, a factor that accounts for all the light outside the bands you directly measured, especially for a cool star that emits a lot in the infrared. That correction depends on the assumed spectrum, which depends on the model atmospheres you use. So now you can see the full stack of uncertainties: distance with errors of tens of percent, extinction with its own uncertainties, effective temperature with a range of a few hundred Kelvin, and model assumptions about how red supergiant atmospheres behave. Each of those steps affects luminosity and temperature, and together they feed into the radius. That's why some researchers look at the famous number around 2,150 solar radii and say this might be an overestimate. But even if you make conservative choices, you still end up in the regime of ridiculously gigantic. Dropping the radius by a third or even by half still leaves you with a star much larger than Betelgeuse, still big enough to engulf the inner solar system. So why does this turn into public arguments about largest star ever? Why is the leaderboard constantly changing? The core reason is that all of these huge red supergiants live in difficult regions. They are dusty, far away, and messy to model. Take Scuti. For a while, it was widely quoted at something like 1,700 solar radii and crowned as the largest known star. Then, better distance and extinction estimates pulled that radius down closer to around 900 to 1,100 solar radii. Canis Majoris went through a similar revision once its distance and brightness were re-evaluated. Stephenson 2-18 jumped into the discussion when new analyses placed it at a large distance and gave it an extreme luminosity and radius, pushing it above most previous candidates. But as soon as you say this might be the largest known star, people immediately ask how solid are the inputs? Is the distance really that high? Is the extinction correction right? Does it really sit in the cluster or is it in front of it? As new Gaia data, improved dust maps, and better models come in, the numbers can shift and candidates leapfrog each other. The largest star title is not a stable crown. It's a moving target that tracks our current best guess. Stephenson 2-18 sits right in the middle of that argument. If the higher distance holds and the cooler temperature is correct, it's absolutely at the extreme edge, maybe over it. If the distance and extinction get revised downward, it drops, and some other red supergiant or hypergiant may take the top spot. Either way, it forces astronomers to confront how fragile their measurements are when they push out into the obscured outer regions of the Milky Way. All of this leads to a deeper, more physical question that you can feel in your gut. If you really do have a star with tens of solar masses spread over up to 10 billion solar volumes, what does that do to basic things like density, surface gravity, and escape velocity? How weak does gravity feel at the surface of a star that big? And how easy is it for that star to literally blow itself apart? How can a star with tens of times the sun's mass feel almost empty when you look at its outer layers? That's the first thing that really breaks your intuition with Stephenson 2-18. Take something like 30 to 50 solar masses, then spread that mass out over roughly 10 billion times the sun's volume. The average density drops to ridiculous levels. You're not dealing with anything like water or rock or even air. The sun's average density is about 1.5 grams per cubic centimeter, a bit denser than water. Now go to Stephenson 2-18. When you divide its mass by that enormous volume, you get mean densities in the range of about 10 to the minus 8 to 10 to the minus 7 grams per cubic centimeter. Earth's atmosphere at sea level is around 10 to the minus 3 grams per cubic centimeter. So the gas spread through Stephenson 2-18's volume is roughly 10,000 to 100,000 times less dense than the air you're breathing. In lab terms, that's closer to a high-quality vacuum chamber than anything that feels like material. Yet this vacuum is hot and glowing. So the star is heavy as a whole, but locally, especially out near the radius we talk about, it's incredibly thin. That sets you up for the next shock. If the density is that low in the outer layers, what does gravity feel like out there? How strong is the pull at the surface of a star this big? Gravity at a surface depends on mass, but it also depends on radius, and it falls off with the square of that radius. The Sun has a surface gravity of about 274 meters per second squared, roughly 28 times Earth's gravity, so about 28 g. Stephenson 2-18 may have 30 to 50 times the Sun's mass, which sounds huge, but its radius is over 2,000 times larger. When you plug that in, the surface gravity drops dramatically into the range of about 1,000th to 100th of Earth's gravity, so between 0.001 g and 0.01 g. That means if you could somehow mark a surface layer and compare, a push that feels normal on Earth would produce a slow drifting motion there. The pull is very weak because you are so far from the bulk of the mass. Even though the total mass is large, the enormous radius wins and gravity gets diluted. But you have to keep one thing clear. There is no hard floor to stand on at that level. This is not a planet with a crust. It's just hot, tenuous gas with low gravity acting on it. So then you ask the next question. If gravity is that weak at the surface, how hard is it for the star to actually hold on to its outer layers? What does it take for gas to escape? That's where escape velocity and stellar winds come in. Escape velocity tells you how fast you'd have to move to break free from the star's gravity and never fall back. For the Sun, that speed at the surface is about 618 kilometers per second, roughly 380 miles per second. Stephenson 2-18 has more mass, but a much larger radius. That combination drops the escape velocity down to only a few tens of kilometers per second at the surface, still far above any human rocket, but relatively low compared to speeds inside the star. Inside a red supergiant like this, gas motions from convection and pulsations can reach several kilometers per second, and radiation pressure from its huge luminosity is constantly pushing outward. When the escape speed is only a few tens of kilometers per second, that combination is enough to drive strong stellar winds. Material gets lifted, pushed, and accelerated until it is no longer bound. That is why red supergiants can lose mass at high rates, on the order of 10 to the minus 5 to 10 to the minus 4 solar masses per year. Over 100,000 years, that's between 1 and 10 suns worth of material stripped away. The star is literally peeling itself apart. Now go back to that idea of standing at the star's radius. Astronomers define the radius at a certain optical depth, basically the layer where the star becomes transparent enough that photons can finally stream out freely. If you could teleport a human body to that layer without instantly destroying it, you would find yourself inside gas so thin that on Earth you'd label it as vacuum. The density is orders of magnitude below our air, but the temperature is a few thousand Kelvin, so every particle that does hit you carries a lot of thermal energy. There is no solid surface to push against, no ground, nothing to rest on. You would just float in a weak gravitational field, surrounded by hot, faintly glowing plasma. For Stephenson 2-18, that surface is simply the place where the star's atmosphere stops being opaque and starts letting light out efficiently. Below that level, densities rise as you go inwards, but you'd still be dealing with very low-density gas for a long way down. The whole outer envelope is a gigantic, diffuse shell, more like a blown-up atmosphere than anything that resembles a rigid object. When you hear radius, it's easy to picture a ball with an edge, but here it really means the level in a wildly extended atmosphere where light can finally escape. So now you can see why the star is so fragile on the outside, and that brings you to the last point in this section. What does such low density and weak gravity do to the stability of the star over time? This configuration is inherently unstable. The envelope is huge, lightly bound, and constantly being pushed around. Convection cells in red supergiants can be enormous, spanning a large fraction of the radius. Pulsations make the star expand and contract slightly, changing brightness and pushing gas in waves. Radiation pressure pushes from the inside out. All these processes jostle the outer layers. In a compact star like the Sun, gravity at the surface is strong enough to keep things tight. In Stephenson 2-18, the same processes act in a much looser environment, so it's easier for parcels of gas to get lifted and never fall back. Over the next few tens of thousands of years, which is a tiny timescale in cosmic terms, Stephenson 2-18 is likely to lose a significant fraction of its mass through these winds and eruptions. The outer layers will drift away to form a slow, dense outflow of gas and dust surrounding the star. That lost mass changes the star's future. It affects how the core evolves, how much mass collapses when it finally dies, and what kind of compact object is left behind. So you have a star that is massive but extremely diffuse, with weak surface gravity, low escape velocity compared to its internal motions, and an atmosphere that is more like a hot vacuum than anything familiar. The next logical question is, if the density is that low and the atmosphere is that fragile, just how bright can this thing be before it literally crosses the line of what theory says is stable? And is Stephenson 2-18 already pushing beyond the usual limits that massive stars are supposed to obey? The size is insane, but the brightness is what really pushes Stephenson 2-18 into dangerous territory, because it is not just large, it is running at a power level that is right up against, or even beyond, what our current theory says is stable for a red supergiant. When you see a line like hundreds of thousands of suns, it's easy to mentally round that off and move on. But here, that phrase is literal. Most estimates put Stephenson 2-18's luminosity somewhere between about 440,000 and 630,000 times the luminosity of the Sun. In metric terms, the Sun puts out about 4 times 10 to the 26 watts of power. Multiply that by 500,000 and you're in the range of 10 to the 32 watts. That is the amount of energy this star is dumping into space every second. To give you a feel for that in a simple way, take every light bulb, every star you see in the night sky, everything powered by the sun here on Earth, then multiply that by hundreds of thousands. That is the scale at which Stephenson 2-18 operates. If you moved it to the distance of Sirius, about 8.6 light years away, the night sky would not look like a dark dome with a bright point. It would glow with a constant, harsh light, because this object is that bright. So you have this combination: ridiculously low surface gravity, very extended radius, and 500,000 suns of power going through that structure. The next natural question is simple. Is there any point where stars just can't sit quietly anymore, where being this bright at this temperature makes the whole thing unstable by default? When astronomers plot massive stars on the Hertzsprung-Russell diagram, the graph of luminosity versus temperature, there's an upper boundary that shows up in the data. It's called the Humphreys-Davidson limit. Above this line, in the region of very high luminosity, stars don't hang around as calm supergiants for long. Instead, they tend to lose mass violently, erupt, or transition to hotter, stripped phases. It's an empirical boundary, meaning it comes from what we observe, not just from pure theory. For red supergiants, that upper boundary in luminosity is roughly around 300,000 to 400,000 times the luminosity of the sun. Below that, you can find stars that live for a while as red supergiants, losing mass but not instantly destroying their outer layers. Above that, the combination of gravity and radiation pressure stops working in a stable way. The star is expected to either blow off a lot of mass or move to a hotter position on the diagram, becoming something like a luminous blue variable or a Wolf-Rayet star. Now put Stephenson 2-18 on that same diagram with the usual numbers. A luminosity in the 440,000 to 630,000 range places it at or above that Humphreys-Davidson limit for its cool surface temperature, around 3,200 Kelvin. That's one big reason why astronomers look at its quoted distance and radius and immediately become cautious. If those more extreme luminosity values are correct, this star is not just near the line, it's sitting over it, in a zone where red supergiants are not supposed to be long-lived. So you get two competing possibilities. One, the parameters are off. Maybe the distance is overestimated, maybe the extinction correction is too aggressive, maybe the temperature is slightly wrong. Any of those would pull the luminosity down, possibly back under the Humphreys-Davidson limit, making Stephenson 2-18 merely an extreme red supergiant, not a full-blown rule breaker. Two, the parameters are mostly right, and the star really is sitting at an ultraluminous low-temperature point where theory says it should be extremely unstable. If the second option is true, Stephenson 2-18 becomes a problem case for massive star theory. It would mean that stars can spend at least some time as ultraluminous red supergiants above the usual limit, with luminosities pushing above 400,000 suns while still remaining very cool and extended. That would force us to rethink how fast such stars lose mass, how quickly they should evolve into hotter phases, and how accurately our models handle the balance between radiation pressure, convection, and gravity in these swollen envelopes. In particular, models often expect very massive stars to move off the red side of the diagram once they get close to that luminosity ceiling. They should lose their outer hydrogen layers, heat up, and become hotter, more compact objects before they explode. But an object like Stephenson 2-18, if its most extreme values hold up, is basically saying, I am still very cool, very large, and yet extremely bright, which squeezes that timeline. Either the star is caught in a very brief extreme phase, or the models underestimate how long such a configuration can last. The tension is clear. If we push the distance and extinction down a bit, the luminosity drops. The star falls back under the Humphreys-Davidson line, and the theoretical picture relaxes. But then you have to explain why different analyses, using different methods, keep landing in that high luminosity range. If we instead accept the high luminosity, we are forced to accept that there are stars living, even temporarily, in regions of the diagram where we did not expect them to stay. So you reach the key question in very simple language. Is Stephenson 2-18 allowed to exist in the form we currently think it has? If it is not, something in our input data is wrong. Maybe it is not really in the Stephenson 2 cluster. Maybe the dust along that line of sight behaves differently than we think. Maybe the spectral modeling of such a cool, extended atmosphere is systematically biased. In that case, the star becomes the motivation to go back and fix our measurements. If it is allowed, and the star really is a red supergiant or hypergiant running at close to 500,000 solar luminosities with a radius around 10 astronomical units, then our theoretical upper limits for red supergiants are incomplete. The Humphreys-Davidson limit would still mark a general boundary, but Stephenson 2-18 would sit right against it as a warning sign that the real behavior of massive stars near that edge is more complicated than a simple line on a plot. Either way, this one object is forcing a check on our equations. It's telling us that out in heavily obscured, massive clusters, stars can evolve into states that are right at the edge of stability, and we may not have the full story of how long they can stay there, how fast they lose mass, or how exactly they die. And that brings up the next high-stakes question. If a star starts its life with tens of solar masses, expands until its atmosphere is barely held together, and shines with hundreds of thousands of suns of power, what is the actual endgame? How much fuel does it have left? How long can it keep burning in these different shells? And when it finally collapses, what kind of supernova and compact remnant will it leave behind? So what actually happens when a star this big runs out of things to burn? What does the last chapter of Stephenson 2-18 really look like? Right now, it's already past the simple part of its life. Core hydrogen is gone. That phase ended millions of years ago. It has almost certainly burned through core helium as well. Inside, the core is now made mostly of heavier elements, and fusion has moved into shells around it. The next fuel in line is carbon. In the hot, dense core region, carbon nuclei can fuse into neon, sodium, magnesium, and other elements. That carbon burning phase is shorter than the earlier ones. It might last thousands of years, not millions. After that, neon burning kicks in, producing more oxygen and magnesium. Then oxygen burning builds silicon and sulfur. And finally, silicon burning builds nickel and iron. Each of these stages happens in a smaller, hotter inner region, with the outer layer still acting like a huge, inflated, unstable envelope. By the time Stephenson 2-18 is fusing silicon, there's not much time left at all. Carbon burning might last thousands of years, neon and oxygen drop to hundreds or less, and silicon burning is down in the range of days. So you go from this phase lasts longer than human history to this phase fits inside a human lifetime to this phase is shorter than a month as the core climbs the periodic table. The star is still losing mass in its outer layers, but deep inside, the core is racing through fuel. That raises the next question. If the early life lasted millions of years, how much time is really left now, and how does that compare to our own timescales? A star like Stephenson 2-18 probably lives only around 5 to 10 million years in total, from birth in a dense cloud to final collapse. That's extremely short compared to the sun's expected 10 billion years. Most of that life is spent in the hot blue main sequence phase, quietly burning hydrogen in the core. Once it leaves that phase and becomes a red supergiant, the clock is already in the late innings. As a red supergiant, it spends maybe a few 100,000 years swollen up, with a very extended atmosphere, strong winds, and shell burning going on inside. In the final tens of thousands of years, the heavy element burning stages start to stack up, and the evolution speeds up. For carbon burning and beyond, you're down to thousands of years, then hundreds, then days. From our perspective, that still sounds long, but in stellar terms, it's a frantic sprint to the finish. The star is burning through complex fusion cycles, shaking its envelope with pulsations and convection, and dumping more and more processed material into space. So the big step you're heading toward is clear. What exactly stops this process, and how does the whole star suddenly switch from fusion powerhouse to catastrophic collapse? The key stopping point is iron. Fusion releases energy when you go from light elements to medium elements like carbon, oxygen, and silicon. But once the core builds up enough iron, that changes. Fusing iron or heavier elements doesn't give you energy back, it costs energy. At that moment, fusion can no longer support the core against gravity. When the core of Stephenson 2-18 reaches that iron-dominated state and grows above a certain mass, gravity wins very fast. The core collapses in a fraction of a second. Densities shoot past anything in normal matter, and the inner core slams down toward nuclear density. That collapse triggers a huge release of energy in the form of neutrinos and a rebound shock. In a successful explosion, that shock wave, aided by the neutrino flood, rips through the star's outer layers. The result is a core collapse supernova. In terms of energy, you're looking at something around 10 to the 44 joules released in the explosion. For a short period, maybe days to weeks, the supernova's visible light can rival or outshine an entire average galaxy. Most of the energy actually goes into neutrinos that pass straight through the outer layers and out into space, but the part we can see is still enormous. The slow, inflated red supergiant instantly becomes a rapidly expanding cloud of superheated gas racing outward at thousands to tens of thousands of kilometers per second, thousands of miles per second. That leads to the next question. After that core collapse, what is left behind in the middle? Does a star this massive leave a dense neutron star, or does it jump straight to something even more extreme? For a moderate mass massive star, the remnant often settles as a neutron star, a ball about 20 kilometers across with more mass than the Sun, packed at nuclear density. But Stephenson 2-18 likely started with 30 to 50 solar masses. Even after losing a lot of that mass through stellar winds and maybe eruptions, the core at collapse is expected to be heavy. In that regime, the remnant almost certainly becomes a black hole rather than a neutron star. In a black hole formation scenario, the inner core collapses directly past the neutron star stage and continues inward until an event horizon forms. A fraction of the outer material is blown away in the explosion, but a significant amount can fall back, feeding the newborn black hole. The final black hole might have something like 10 to 20 times the Sun's mass, maybe more depending on how much mass the star lost in winds before the explosion and how much falls back afterwards. That black hole becomes a long-lived, invisible remnant detectable only through its gravity or through any accretion activity if it later pulls in gas or a companion. All of this is dramatic on paper, but you're watching from Earth, 20,000 light-years away and behind a lot of dust. So the simple question is, would you even notice when Stephenson 2-18 finally goes off? At a distance of about 18 to 20,000 light-years, and with heavy dust in the way, the supernova would not light up our sky like a second sun. It probably would not rival the full moon the way a Betelgeuse supernova might if Betelgeuse blew up at its 200 to 700 light-year distance. The dust along the line of sight to Stephenson 2-18 would dim the visible light heavily. To the naked eye, if it were visible at all, it might appear as a new star or a modestly bright point for a while, not as a blinding beacon. But in other channels, it would be a huge event. Neutrino detectors on Earth would see a sharp burst of neutrinos arriving within seconds of the core collapse, long before the light fully brightened. Infrared telescopes would see the supernova more clearly than optical ones, because dust is more transparent to infrared. Radio and X-ray observatories would track the shock wave as it slams into the dense material the star has been shedding for thousands of years. For astrophysics, it would be a goldmine of data. In terms of danger, the distance keeps you safe. At roughly 20,000 light-years, even a powerful core collapse supernova is too far to seriously affect Earth's biosphere. The radiation and high-energy particles would be diluted over a huge volume of space. For us, the only impact would be a spike in neutrinos in detectors, extra work for astronomers, and a lot of excitement. The timing is the one part that doesn't fit human thinking very well. Soon in cosmic language means within the next few 100,000 years. Stephenson 2-18 could explode tomorrow on that scale or in 300,000 years, and that still counts as soon compared to its total lifetime. For you, practically, that means never. From our perspective as a species, we are almost certainly not going to see it. But the physics says the star is already deep into its final slow-motion collapse phase, so the end of Stephenson 2-18 is basically locked in, a race through the last fusion stages, core collapse, a supernova that seeds its surroundings with heavy elements, and the black hole sitting quietly in the aftermath. Before that happens, though, there is another slow, destructive process already underway. How does a star this big gradually strip away its outer layers, build a dense cocoon of gas and dust around itself, and set up the conditions that will shape how that final explosion actually looks? How fast is Stephenson 218 actually tearing itself apart? You already know its outer layers are weakly held, but the numbers for how much mass it is dumping into space are brutal. Red supergiants in general can lose material at rates of around 10 to the minus 5 to 10 to the minus 4 solar masses per year. In normal words, that is between 100,000th and 1/10,000th of the sun's mass every year. Take the upper end, 10 to the minus 4 solar masses per year. Over 100,000 years, that adds up to about 10 times the sun's mass blown out as wind. Even at the lower rate, you still lose about 1 solar mass in that time. So if Stephenson 218 started somewhere around 30 to 50 solar masses, it can shed a large chunk of that, multiple suns worth of material, just by leaking gas through a slow, dense wind over its red supergiant lifetime. You're not looking at a gentle breeze. You're looking at a continuous outflow of gas moving at tens of kilometers per second, tens of miles per second, flowing off the star in all directions. So the star is constantly feeding the space around it with its own outer layers. The next step is, what happens to that material as it moves away and cools? Because it does not stay as a pure hot gas forever. As the wind moves outward, it expands and cools. Close to the star, the gas is too hot for solid particles to exist. Everything is ionized or in simple molecules. But further out, at distances where the temperature drops to a few hundred to around 1,000 Kelvin, atoms and molecules can start to stick together and form dust grains. These grains can be made of silicates, carbon compounds, or other elements produced in the star. Once dust forms, the nature of the outflow changes. Dust grains are very good at absorbing visible and ultraviolet light coming from the star, and very good at re-emitting that energy in the infrared. So a thick, dusty envelope around Stephenson 218 will soak up a lot of its visible light, and then glow strongly at longer wavelengths. That is why stars like this have what astronomers call an infrared excess. Compared to a clean, dust-free star at the same temperature, they look much brighter in the infrared bands. This is exactly why Stephenson 218 and its cluster neighbors jump out in infrared sky surveys. In visible light, they are heavily divvied by interstellar dust plus their own dusty envelope. In infrared, both those obstacles are much less severe, so the star suddenly looks like a very bright object. To an infrared survey, it is a beacon. To a normal optical telescope, it is almost hidden. Now, think about what this steady outflow is doing to the space around the star over tens or hundreds of thousands of years. You're not just filling nearby space with random gas. You're building a structured environment that the future supernova will have to explode into. By the time Stephenson 218 actually collapses, it will be sitting inside a cocoon of gas and dust that it created itself. The density of that cocoon will not be perfectly smooth. Mass loss in red supergiants is often clumpy and variable. There can be slower and faster periods, denser and thinner shells, maybe even asymmetries where one side is heavier than another. All of that structure is sitting there, waiting. When the core finally collapses and the star explodes, the shockwave and the expanding ejecta will crash into this circumstellar material at thousands of kilometers per second. That collision will heat the gas to very high temperatures, generating X-rays and strong radio emission. The shape and brightness of the supernova's light curve and the details in its spectrum will be strongly influenced by how much material is around the star and how it is arranged. A thicker, denser wind can make the supernova brighter for longer and can add narrow emission lines from shocked gas. A thinner, cleaner environment leads to a different signature. We've already seen this kind of connection in real objects. Type 2P supernovae, which come from red supergiant progenitors, show clear links between pre-explosion mass loss and the way their light curves behave. When we manage to identify a red supergiant in pre-explosion images and later see the supernova, we can connect the dots: mass loss, circumstellar density, and final explosion shape. Stephenson 218 as an extreme case is important here because it sits at the upper edge of mass and luminosity. Understanding its winds tells you what kind of blast environment such a monster sets up before it dies. That leads to another obvious question. Is Stephenson 218 unique in this violent peeling process, or do we see similar behavior in other extreme red supergiants? We already have examples like VY Canis Majoris, a huge red hypergiant in Canis Major. High-resolution images show arcs, clumps, and asymmetric shells of gas and dust around it, clear signs of episodic mass loss events. Instead of one smooth wind, it looks like the star has had multiple outbursts, throwing off large chunks of atmosphere in different directions. UY Scuti and other giants also show signs of complex circumstellar material. These stars do not just blow a steady, uniform wind. They cough, pulse, and erupt, and the result is a messy nebula around them. Stephenson 218 probably does the same kind of thing, but there are two big complications. It is much farther away than VY Canis Majoris, and it sits behind heavy interstellar dust. That makes detailed imaging extremely hard with current instruments. We mainly detect its overall brightness and colors in the infrared, not fine structure in its outflows. It is very likely that if you could resolve the region around it with future infrared and radio telescopes, you would see arcs, shells, and clumps similar to what we see around closer hypergiants, maybe even more extreme. So right now, we treat Stephenson 218 as a sort of hidden version of stars like VY Canis Majoris, doing the same violent mass loss work, but concealed behind layers of dust and distance. Upcoming facilities, especially more sensitive infrared space telescopes and giant ground-based telescopes with adaptive optics, should be able to probe its surroundings better, map its winds, and maybe catch evidence of recent eruptions. The bottom line is simple. Stephenson 218 is not just big, it is actively dismantling itself. Every year, it throws more of its own outer layers into space, builds a dense, dusty environment, and sets up the conditions for a highly structured, high-energy supernova later on. And that raises a sharp question for the next part of the story. How did we even find the star doing all of this, buried behind dust and a crowded spiral arm, and what does that say about how many other too big stars are still hiding in the Milky Way waiting to be discovered? How do you even notice a star like Stephenson 218 when it's buried behind dust, sitting in a crowded spiral arm, and not especially impressive in visible light? The answer is you don't start by looking at the star itself. You start by mapping the sky in the right wavelengths and let the data point you to weird patches. That's what wide-field infrared sky surveys did. Projects that scanned the whole sky in the near-infrared built huge catalogs of sources, each with brightness measured at several wavelengths. When astronomers combed through those catalogs in the direction of the inner Milky Way, they spotted clumps of very bright, very red objects that didn't fit the patterns of ordinary stars. One of those clumps turned out to be the cluster now called Stephenson 2. Those early survey maps were not trying to find the largest star, they were just mapping. But once you see a bunch of sources all close together on the sky, all very bright in the infrared and all heavily reddened, that's a hint of a massive embedded cluster. Follow-up work zoomed in on that region, confirmed there was a real overdensity of bright red stars, and started piecing together that this wasn't just a random grouping. It was a real physical cluster, packed with red supergiants around 18 to 20,000 light-years away. Stephenson 218 first shows up in that context, as one member of a list of very luminous, very red objects in that cluster field. Once you have a suspected cluster, the next question is, which of these points are actually red supergiants and which are just normal stars or background objects? You have to sort them. That's where color and brightness cuts come in. In infrared color magnitude diagrams, red supergiants stand out. They are intrinsically bright, so even after heavy extinction, they still appear bright in the infrared, and their colors fall in a range that marks them as cool, luminous stars, rather than faint dwarfs. Astronomers look for sources that are both very bright in, say, the K-band, around 2.2 micrometers, and very red in combinations like JK or HK, which are simple differences between two bands. Objects that hit those thresholds are flagged as candidates. In the Stephenson 2 field, there are dozens of such points. Stephenson 218 sits near the extreme end, among the brightest and reddest. That's the first sign that it might be one of the most luminous cluster members, and possibly an especially large red supergiant. But color and brightness alone are not enough. You still need to know what kind of star it really is. So the next step is clear. You point spectrographs at these candidates and ask, what do their light look like when you spread it into a spectrum? Because that's what tells you spectral type and temperature. For Stephenson 218 and the other cluster members, follow-up spectroscopy shows strong molecular absorption bands, especially from titanium oxide, which is typical of cool M-type stars. The depth and pattern of those features tell you it's not a small M dwarf, but a luminous supergiant. So you tag it as something like an M6 red supergiant. From that classification, plus its colors, you infer an effective temperature of around 3,200 Kelvin. The spectrum also shows broad features and gravity-sensitive lines that separate giants from supergiants. Supergiants have lower surface gravity, and that leaves fingerprints in the line shapes. When you match what you see to standard templates, Stephenson 218 lands firmly in the extreme red supergiant box. That combination of very luminous infrared brightness, heavy reddening, and a late M supergiant spectrum is what marks it as one of the most extreme stars in the field. Once you know the type, you can refine estimates of temperature and bolometric corrections, which then feed into luminosity and radius estimates. But before you commit, you still have to answer a crucial question. Is this star actually part of Stephenson 2, or is it just lined up in the same direction by chance? That's where kinematics and membership tests come in. Astronomers measure radial velocities, how fast a star is moving toward or away from us along the line of sight, using the Doppler shift of spectral lines. Members of a cluster tend to share similar radial velocities because they formed from the same cloud and moved together through the galaxy. They also sit in a narrow range of position on the sky, in galactic longitude and latitude. For a cluster this distant and dusty, proper motions, these sideways motion across the sky, are small and hard to measure accurately, though modern missions can help. But radial velocities are accessible. When you check stars in the Stephenson region, many of the bright red supergiants show similar radial velocities, strengthening the case that they belong to a common group. Stephenson 218's measured velocity is roughly in line with this set, which is why several studies treat it as a probable cluster member. Still, the uncertainties are large enough that some researchers argue you cannot be completely sure. If its true radial velocity or distance is somewhat different, Stephenson 218 could be a foreground star, a massive red supergiant closer to us, just projected onto the same line of sight. That possibility is a big piece of the largest star controversy. If it's a cluster member, its inferred luminosity and radius stay extreme. If it's a foreground object, those values drop. So even at the membership stage, the data are good enough to make a strong case, but not so perfect that there is no debate. That brings you to the last and maybe most unsettling question in this chain. If it took all this work, infrared surveys, color cuts, targeted spectroscopy, kinematic checks, just to nail down one cluster and one candidate largest star, how many similar or even more extreme stars are still hidden? The Milky Way's disk is full of dust lanes and crowded fields, especially toward the inner galaxy. Infrared surveys have revealed many massive clusters that were completely unknown in visible light, and we are still adding to that list. Some clusters sit farther away than Stephenson 2, behind even thicker dust. In those regions, we only see the very brightest members, and our ability to classify them is limited by resolution and signal quality. It's entirely possible that there are red supergiants or hypergiants even more extended than our current record holders, sitting in distant clusters we have barely resolved, or in parts of the galaxy we have not probed deeply in the right wavelengths. Stephenson 2-18 is basically a proof of concept. Dust can hide a star large enough to swallow most of our solar system, and we only found it because infrared surveys happened to map that region with enough depth. Future surveys, better infrared instruments, and higher precision astrometry will almost certainly uncover more of these extremes. Some will turn out to be smaller than early estimates. Others may push the limits even further. So the discovery story leaves you with a simple, sharp tension. If dust and distance can hide a star like Stephenson 2-18 until fairly recently, what else is still out there in the Milky Way, sitting behind one more layer of dust, just beyond the reach of our current instruments, waiting to mess with our idea of how big a star can really get? So, who actually holds the title of largest star right now, and why does that title keep slipping away every few years? For a long time, Stephenson 2-18 wasn't even in the conversation. The giants you heard about were names like VY Canis Majoris, UY Scuti, and before that, a whole list of oversized red supergiants that textbooks love to show as bigger than the solar system. Each generation of data crowned a new champion. Then better measurements came in and quietly knocked it down. Early on, some of the first largest star candidates were extreme red supergiants with very uncertain distances, objects like V354 Cephei or KW Sagittarii. Their radii were quoted at well over 1,000 times the sun's radius based on rough distance estimates and crude extinction corrections. They became popular examples in books and outreach talks. Then, VY Canis Majoris, a dusty red hypergiant in Canis Major, grabbed attention with estimates of around 1,400 to 2,000 solar radii, depending on which paper you read and which distance you assumed. For a while, that was the big monster everyone pointed to. But all of those early candidates shared one weakness: their distances were poorly known. They sit in crowded, dusty regions of the Milky Way, and the methods used to estimate distance were indirect and noisy. That meant the derived luminosities and radii were on shaky ground. As long as the distances were uncertain, the largest star list was basically a set of educated guesses. Then, missions like Gaia started to sharpen the picture for some of them, and the corrections were brutal. This is the pattern you need to see. Once you start revising distances with better data, how fast do these giants fall down the ranking? When you get a more accurate distance that is smaller than the old estimate, the true luminosity goes down with the square of that distance, and the radius drops with the square root of that change, just like we talked about earlier. That is exactly what happened to several famous giants. Improved parallaxes or better modeling of the line of sight dust pulled their distances in, so the stars turned out to be less luminous and less physically large than we thought. They're still huge by normal standards, but they lose the extreme edge. UY Scuti is the cleanest example to look at here. For a while, UY Scuti was widely advertised as the largest known star, with a quoted radius of around 1,700 times the sun's radius. That figure came from older distance estimates and photometry that made it look incredibly luminous. Once better constraints on its distance and extinction arrived, that radius got revised down hard. More recent work puts UY Scuti's radius in the ballpark of about 900 to 1,100 solar radii. That is still enough to engulf Mars and possibly push out near Jupiter's orbit, but it's a big difference from the earlier claims. One adjustment in distance and extinction, and the largest star crown slipped away. So now you can see the trap. The stars that seem to be the biggest are often the ones with the messiest data, and as soon as you clean up the inputs, the claimed radius shrinks. That's exactly the same vulnerability Stephenson 2-18 has, even though right now it sits near the top. So why did Stephenson 2-18 suddenly jump into the spotlight if other giants were already famous? The reason is simple. When analysis teams analyzed the Stephenson 2 cluster using infrared data and modeled the stars as red supergiants at a distance of about 5.5 to 6 kiloparsecs, Stephenson 2-18 came out as one of the brightest members. Combine that with a cool surface temperature around 3,200 degrees Kelvin, and the luminosity estimate lands in the few 100,000 suns range. Feed that into the radius calculation, and you get numbers around 2,150 solar radii. That one step, assume Stephenson 2-18 is at the Stephenson 2 cluster distance, is what launches it past earlier candidates like UY Scuti, at least on paper. On that assumption, UY Scuti's revised radius of roughly 900 to 1100 solar radii suddenly looks modest. VY Canis Majoris moves into similar range, and Stephenson 2-18 sits out in front with a radius close to 10 astronomical units. So it isn't that our measurements for UY Scuti got worse, it's that those measurements improved and shrank its size at the same time that Stephenson 2-18 arrived with a fresh, very large estimate. But you already know the catch. Stephenson 2-18's huge radius partly comes from older or less precise distance and extinction assumptions too. It shares the same problem that sank UY Scuti's earlier numbers. If future Gaia-like data or better infrared astrometry show that Stephenson 2-18 is closer than the Stephenson 2 cluster, or if the dust along that line of sight is mischaracterized, its luminosity will drop and the headline radius will follow. It could fall back into the same range as other big red supergiants. So that leads to the real point you should take from this size war. The leaderboard is not settled, and it probably never will be in a permanent way. The largest star title is not like the tallest building where you can measure the top with a laser and be done. It's a moving target, constantly updated as we get better distances, better dust maps, and better atmospheric models. Today, depending on which papers you trust, you could argue for Stephenson 2-18, or you could still point to other hypergiants like VY Canis Majoris, or even newly analyzed candidates in other dusty clusters. Tomorrow, another star in an even more obscured region could get a revised distance that suddenly puts its radius above all the rest. Or a more careful analysis could knock Stephenson 2-18 down, just like UY Scuti was knocked down. The only stable conclusion is that there are stars out there with radii on the order of thousands of solar radii and volumes billions of times that of the Sun, and we are still sorting out which one is technically the biggest at any given moment. So instead of thinking, this is the one largest star, full stop, the better mindset is, here's a group of extreme red supergiants and hypergiants all pushing at the limits of what massive stars can do, and Stephenson 2-18 is one of the most aggressive cases we've seen so far. The competition isn't really between the stars, it's between our measurements and our models, and every time we refine them, the rankings change. And that raises a deeper, more important issue than any leaderboard. If one of those stars can already swallow most of the solar system, how does one single object like that affect the galaxy around it? How much heavy material does it make? How much gas does it stir? And what does its death actually contribute to the Milky Way's long-term evolution? You've seen how absurd Stephenson 2-18 is as an object, but why should you care about one star that's going to die far away and long after you're gone? Because stars like this are the main way the universe builds the stuff you're made of. This isn't just a freak show. This is the kind of engine that turned a hydrogen-helium universe into one that can make rocky planets, metal, and biochemistry. Start inside the core. By the time Stephenson 2-18 is in its late red supergiant phase, the inner regions have already manufactured a whole staircase of heavier elements. First, core hydrogen burning built up helium. Then core helium burning made carbon and oxygen. Later, carbon burning added neon, sodium, and magnesium. Oxygen burning built silicon and sulfur. Silicon burning piled up nickel and iron group elements. So in that tiny central region, maybe only a few thousand kilometers across, you have a compact onion of layers, each rich in different elements, sitting underneath an envelope that stretches over billions of kilometers. The core is where most of the heavy elements you care about are actually forged. When you read that a massive star can eject several solar masses of oxygen or a solar mass of silicon and iron, that is what you are looking at, the end result of all those fusion stages. Now, the obvious question, if all the interesting elements are buried in the core, how do they ever get out into the galaxy where they can build anything? Two channels do the work. The first is slow and steady, those red supergiant winds you heard about. Over hundreds of thousands of years, Stephenson 2-18 will blow off a few to maybe 10 solar masses of material. That wind is not pure hydrogen. It carries carbon, nitrogen, oxygen, and heavier elements that have been dredged up from the interior by convection and mixing. A lot of that material forms molecules and dust grains in the outflow. The second channel is the supernova. When the core finally collapses and the explosion tears the star apart, the shock wave rips through those fused layers and throws them into space. In a typical massive star supernova, you can eject several solar masses of oxygen, maybe around one solar mass of silicon and sulfur, and a fraction of a solar mass of iron group elements, among other things. In metric terms, that's something like 2 times 10 to the 30 kilograms of oxygen, and comparable amounts of other heavy elements being dumped back into the surrounding gas. So each time a star like Stephenson 218 dies, it injects raw material for future planets, atmospheres, and rocks into the interstellar medium. The galaxy doesn't just recycle gas, it gets richer in heavy elements every time one of these giants explodes. That leads straight into the next point. These giants don't just enrich the gas, they also physically push it around. So how does that change star formation in the long term? When Stephenson 218 blows up, it will send the shock wave out into the surrounding region at thousands of kilometers per second, thousands of miles per second. That shock will plow into the gas and dust that the star and its neighbors have already shed, and then into the wider molecular cloud material in the spiral arm. As it sweeps through, it compresses pockets of gas. When those pockets reach high enough densities, gravity takes over and they collapse into new stars. On larger scales, supernovae carve out hot, low-density bubbles and push on the edges of cold clouds. You can picture, not in a poetic way, but in a literal physical way, shells of compressed gas forming where multiple shock fronts meet. Those shells are where new clusters and new generations of stars are likely to form. So a star like Stephenson 218 doesn't just end its life with a bang and disappear. Its winds and its final explosion drive turbulence and compression in the Milky Way's gas, helping to seed the next round of star formation. Over tens of millions of years, many massive stars exploding in a region can completely reshuffle the gas, creating cavities, filaments, and dense knots where future stars will ignite. Now connect that to something very close to you. If massive stars are producing and spreading heavy elements like oxygen, silicon, and iron, what does that have to do with your body and the ground you stand on? Every rocky planet you've ever heard of, including Earth, is built out of heavy elements. Earth's crust is loaded with silicon and oxygen. Its core is mainly iron and nickel. The calcium in your bones, the oxygen in your lungs, the phosphorus in your DNA, the iron in your blood, all of that had to be made in stars that went through exactly this kind of massive star cycle. Hydrogen and helium came from the Big Bang, but virtually everything else, carbon, nitrogen, oxygen, silicon, iron, was cooked and ejected by earlier generations of massive stars. That means the elements making up your body were once locked inside stars that looked a lot like Stephenson 218. Maybe not exactly as extreme, but in the same class of high-mass, short-lived giants. Those stars formed, burned through their fuel in a few million years, blew up and sprayed their cores into space. That debris mixed into the cold clouds that later collapsed to form the Sun and its planets. When Earth formed about 4.5 billion years ago, it inherited that mix, and everything you see today is built from it. Put numbers on it. A single massive star supernova can eject, for example, 2 or 3 solar masses of oxygen. That is several times the mass of the Sun in just one element. Over the history of the galaxy, millions of such explosions have gone off. The Milky Way has had over 10 billion years to let this process run. The result is a disk where a noticeable fraction of the mass is now in elements heavier than helium, enough to build billions of Earth-sized planets and who knows how many complex chemistries. So when you talk about Stephenson 218's legacy, you're not talking about a pretty nebula image. You're talking about actual material that will someday end up in solid surfaces, atmospheres, and possibly biochemistry. In the Milky Way's long timeline, this star's death will be just one more event in a chain of enrichment steps. It will add oxygen, silicon, iron, and other heavy elements to the Scutum Centaurus arm's gas. Later, that gas will collapse into new stars, some with planets, some without. On at least some of those planets, complex chemistry will get a chance to run. So you can frame it very bluntly. Stephenson 218 is one more link in the chain that built worlds like Earth. You're seeing it near the end of its life, but everything it has fused in its core is future raw material for planets and maybe for life. That raises a sharper question that brings the scale back to your personal point of view. If a single star like this can reshape its local region and supply the raw material for new planets, what would it actually mean for us if a star this powerful were sitting much closer, lighting up our sky, stripping mass, and eventually exploding just a few hundred light years away instead of 20,000? So, what would life actually look like if a star like Stephenson 218 wasn't sitting safely 20,000 light years away, but parked much closer, in the same neighborhood as Betelgeuse? Right now, it's so far and so obscured that you never notice it, but shift it inwards to a few hundred light years, and suddenly it becomes a permanent, in-your-face object in the sky. Take Betelgeuse's rough distance, a few hundred light years, say about 600 light years for simple numbers. At that distance, a red supergiant with a luminosity of a few 100,000 suns would be insanely bright in our sky. The received light from a star falls off like 1 over distance squared. Move Stephenson 218 from 20,000 light years to 600 light years, you're cutting the distance by about a factor of 30. That boosts its apparent brightness by about 30 squared, roughly a factor of 900. Right now, you can't see it with your eyes at all. At 600 light years, it would dominate its part of the sky. It would look brighter than any star you've ever seen. It would probably be a negative magnitude object, bright enough to cast faint shadows on dark nights, especially from a really dark site. So what does that do to the human experience of the sky, day to day? At night, you look up and see a huge red star, not resolving as a disk to the naked eye, but clearly brighter and redder than anything else. It would never be a subtle point. In very dark conditions, you might be able to see your own shadow from its light alone. It would change the feel of the night sky completely. Cultural stories, navigation, everything humans have ever tied to bright stars would revolve around this one object. But what about the daytime? Does something that bright change your daylight environment? Compared to the sun, even a 500,000 sun star at hundreds of light years is still extremely faint. The sun is one astronomical unit, about 150 million kilometers, while Stephenson 218 at 600 light years is nearly 6,000 trillion kilometers. When you run that distance ratio through the same 1 over distance squared rule, the actual energy hitting Earth from Stephenson 218 is still tiny compared to sunlight, even if it looks very bright at night. So it messes with your nights, not your daytime climate. The next question you care about is obvious. If it's that bright, is it dangerous? Does the radiation from a nearby red supergiant hurt habitability? In its current red supergiant state, even at a distance of a few hundred light years, the main effect is light, not lethal radiation. Most of the energy is coming out in visible and infrared wavelengths. The ultraviolet output per square meter at Earth would be small compared to the sun, because of the huge distance, even though the total luminosity is huge. So as long as Stephenson 218 is just sitting there as a red supergiant, it's visually dramatic but not a biological threat at a few hundred light years. The real concern comes at the moment of core collapse when you get the supernova. So what does a core collapse supernova do to a planet like Earth if it goes off at a few hundred light years? And at what point does it cross from spectacular light show into serious problem? Rough order of magnitude estimates say that a core collapse supernova at a distance of a few hundred light years could light the sky up to something like the brightness of the half moon, maybe more, for days to weeks. You would see it in the daytime as a star-like point. At night, it would be impossible to ignore. It would be bright enough to affect circadian rhythms in animals and humans if it stayed up for long stretches of the night. But in terms of biological danger, a few hundred light years is probably still in the safe but impressive zone. The high-energy photons and cosmic rays are diluted over such a large sphere that the dose Earth gets is much lower than what you'd need to sterilize the surface. You might get modest effects on the upper atmosphere, slight changes in ionization levels, maybe a tiny uptick in radiation at ground level, but nothing that wipes out life. Start moving that event closer, though, down to a few tens of light years, and you begin to hit uncomfortable numbers. At distances of 10 to 30 light years, models suggest that the burst of high-energy photons and cosmic rays from a supernova could significantly alter Earth's ozone layer. Ozone is what screens out the sun's most dangerous ultraviolet radiation. Strip a large fraction of it, and the surface UV levels jump, damaging DNA, increasing mutation rates, stressing ecosystems, and hitting surface and shallow ocean life hard. You're still not guaranteed a full sterilization, but you're in the territory of mass extinctions and long-term ecological disruption. So you can set up a rough rule of thumb. Supernova at thousands of light years, basically zero direct biological impact. At a few hundred light years, intense spectacle but likely safe in terms of life. At a few tens of light years, serious ozone depletion and real biological stress. Below that, you really don't want to be around. Now plug Stephenson 2-18 into that. At its actual distance, around 18 to 20,000 light years, it is way outside any dangerous range. Even when it finally explodes, the energy reaching Earth will be so diluted that we will only notice it with telescopes and detectors. At a few hundred light years, it would be bright enough to dominate the sky, and its supernova would be one of the brightest events humans could see, but still unlikely to sterilize anything. At a few tens of light years, it would be a legitimate concern for Earth's biosphere. But the key point is simple and reassuring. Stephenson 2-18 is nowhere near that close. It's parked on the far side of the inner Milky Way arm from us. The light it emits now has traveled about 20,000 years before reaching you, and the future supernova's flash will be just as delayed. The physical distance is so huge that its danger is effectively zero. So you're lucky in two ways. First, you live in a relatively quiet arm segment with no Stephenson 2-18 class monster close enough to be a threat. And second, you live at a time when you have instruments that can see these things at safe distances, so you get all of the knowledge and none of the personal risk. That leads you straight to the next big piece of this story. If safety is not the issue, precision is. Our biggest problem with Stephenson 2-18 is that we don't know its distance and size as well as we'd like, because it lives in a dusty region where our current instruments struggle. So what will it actually take to nail those numbers? What kind of next-generation telescopes and observatories do we need to finally say with confidence whether this star really is as big and bright as we think it is, or whether it's about to be downgraded the way past largest star candidates were? Right now, the biggest problem with Stephenson 2-18 is simple. We are still guessing more than we like, so the next step is clear. We need better distance measurements, better temperature estimates, and better ways to see through dust. Everything about this star's largest ever status hangs on those numbers. If the distance drops, the luminosity and radius drop. If the extinction is wrong, the luminosity shifts again. So the future of giant star hunting is basically the future of precision measurement. Distances come first. To really lock a star down, you want parallax, the tiny wobble in position as Earth orbits the Sun. That gives you a geometric distance, not something model-dependent. For stars a few hundred or a few thousand light years away, that works well with current instruments. For stars at 20,000 light years, the parallax angles are so small that we're at the edge of what we can do. For Stephenson 2-18, a clean parallax would immediately tell you if it sits at around 6,000 parsecs, roughly 19 to 20,000 light years with the Stephenson 2 cluster, or whether it's significantly closer, which would slash its luminosity and radius. Without that, you're stuck building distance from indirect methods. This is where you run into Gaia's limits. Gaia is fantastic in the optical, and it has already transformed our view of nearer giant stars. But Gaia struggles in exactly the kind of environment Stephenson 2-18 lives in, crowded, dusty, in the inner disk of the Milky Way. Heavy extinction means the star is faint in Gaia's bands. Blending and confusion with neighboring stars can corrupt the astrometry, and the parallax solution becomes noisy or useless. For some red supergiants, Gaia has already provided better distances and shrunk their radii. For heavily obscured targets like Stephenson 2-18, its impact is much more limited. So the next logical move is to take astrometry and detailed observations into the infrared, where dust is a lesser problem. That's where JWST comes in. The James Webb Space Telescope operates primarily in the near and mid-infrared, from about zero point 0.6 to 28 micrometers. In that range, dust extinction is dramatically lower than invisible light. For a region like the Stephenson 2 cluster, JWST can see many more stars more clearly separated and measure their brightness across a wide range of wavelengths. JWST won't magically fix every distance on its own, but it can do a few crucial things. First, it can give you very accurate spectral energy distributions for cluster members, allowing much better extinction corrections and bolometric luminosities. Second, over many years of operation, repeated JWST pointings can contribute to infrared astrometry, especially when combined with other facilities. Even modest improvements in distance and extinction for the cluster would tighten the luminosity and radius of Stephenson 2-18 dramatically. Third, its spectroscopy can refine temperature estimates by resolving detailed molecular features in these cool, complex atmospheres. On the ground, the next big tools are the extremely large telescopes, the new generation of 25 to 40 meter class telescopes like the ELT, GMT, and TMT. With adaptive optics, these telescopes will deliver very fine angular resolution in the near infrared, and they will collect huge amounts of light. For nearer red supergiants, those telescopes, combined with interferometry, can directly measure angular diameters. You then combine that tiny measured size on the sky with a distance to get a physical radius in kilometers. That skips a lot of indirect inference. For Stephenson 2-18, which is far away, even these telescopes will not cleanly resolve its disk in a simple way. The angular size is just too small. But they can resolve crowded fields in and around obscured clusters, separate overlapping stars, and get high signal-to-noise spectra for many cluster members at once. They can also work with interferometric arrays, like upgraded versions of the VLTI or Cara, to push angular size measurements further than we can now. Even if you can't resolve Stephenson 2-18 itself, you can resolve and characterize closer benchmark giants, nail down the physics of their atmospheres and mass loss, and then apply those improved models to more distant stars. So the future of largest star work looks like this: better parallax in the infrared for obscured clusters, better extinction maps built from multi-wavelength data, higher resolution spectra that pin down temperatures and atmospheric properties, and direct angular diameter measurements for nearer giants that calibrate our entire method. Once that system is in place, the big questions around Stephenson 2-18 will finally move from speculation to hard numbers. And here's the key tension you should hold in your head. Those future measurements might downgrade Stephenson 2-18, the way Scuti was downgraded. If its distance turns out to be smaller, its luminosity shrinks, and its radius could drop into the range of other big red supergiants. It would still be huge, but no longer at the bleeding edge. On the other hand, those same tools might reveal even more extreme stars and even more buried clusters, objects in the far side of the galaxy with radii beyond anything we've put in our diagram so far. Either way, the direction is clear. The combination of JWST, the ELTs, and improved interferometry will make the phrase "largest known star" a much more precise claim. Sometimes the answer will be, we overestimated, it's smaller than we thought. Other times it will be, no, this really is as big and bright as the early number said. Stephenson 2-18 is right on that knife edge. It could become the classic case of a record that didn't survive better data, or it could become the benchmark for what a star at the absolute upper end of size looks like. So you're in an interesting moment. Right now, your mental picture of Stephenson 2-18 is built from large error bars and a lot of indirect reasoning. In 10 or 20 years, with a full set of infrared astrometry, high-resolution spectra, and better models, that picture will either tighten into a confirmed monster or it will shift into something a little less extreme. But even if it shrinks, the basic lesson holds. Stars can reach solar system scale. They can operate at hundreds of thousands of times the sun's power, and they can push right up against what our equations say is possible. And that sets up the next step in the story. Once you've spent this much time talking about a handful of monsters that break the charts, what does that do to your picture of a normal star? How far off is your intuition if your brain keeps defaulting to the sun as typical, when statistically, most stars are nothing like it, and objects like Stephenson 2-18 sit out in the extreme tail of the distribution? When you hear star, your brain probably plugs in the sun's numbers by default. 1.4 million kilometers across, about 860,000 miles. Neat ball of hot plasma in the center, planets doing laps around it. Stephenson 2-18 wrecks that shortcut. Here you have a single star with a radius of about 1.5 billion kilometers, around 930 million miles, so big that its surface would sit near Saturn's orbit if you dropped it into our system. In that setup, the solar system is no longer a star with planets, it's a star that fills most of the space where planets used to be. That is the first way these giants break your intuition. They push the stellar scale up to the solar system scale. You're used to thinking star in the middle, planets outside. With Stephenson 2-18, the outside for planets like Earth, Mars, even Jupiter is gone. They end up inside the star's atmosphere. You don't need a sci-fi scenario to do that. You just need a star with a radius of something like 10 astronomical units. That's not a rare structure in a galaxy, that's a single object. Then there's the way size, brightness, and temperature trade off. Your everyday logic says brighter means hotter, but Stephenson 2-18 is cooler on the surface than the sun, roughly 3,200 Kelvin versus the sun's 5,800 Kelvin, and still pumps out hundreds of thousands of times more power. The reason is simple once you say it. The total power depends on both the surface temperature and the total area that's radiating. So if you spread that emission over a huge area, like a sphere with a radius over 2,000 times the sun's, you can keep the temperature relatively low and still get a gigantic total luminosity. It's the opposite of a tiny hot blue star. A tiny hot blue star has a very high temperature, but a small surface and ends up with a moderate luminosity. A huge, cool red star like Stephenson 2-18 has a lower temperature, but such an absurdly large area that the total comes out huge. Once you get that, you stop thinking bigger star means hotter surface and start thinking bigger star picked size as its way to get bright. This also changes how you think about power per unit area. The sun's surface is hotter and radiates more intensely from each square meter. Stephenson 2-18 surface is cooler. Each square meter is weaker, but there are so many more square meters that, added up, the total wins. It's a very different configuration. Low-intensity radiation spread over a giant shell. Now, tie that back to lifetimes, because mass, energy output, and lifetime are tightly linked, and your intuition is probably wrong there too. The sun, with one solar mass and a moderate luminosity, can stay on the main sequence for around 10 billion years. It burns its hydrogen slowly and efficiently. A star like Stephenson 2-18, starting at 30 to 50 solar masses and shining at hundreds of thousands of solar luminosities, races through its fuel. Roughly, the lifetime on the main sequence goes something like mass divided by luminosity. If you increase the mass by, say, a factor of 40, but the luminosity by a factor of 400,000, the main sequence lifetime shrinks by a factor of 10,000. So instead of billions of years, you get a few million. By the time the sun has finished only a few tenths of 1% of its life, a Stephenson 2-18 type star has already burned through core hydrogen, burned through core helium, and moved into late stages. That's another way these giants flip your expectations. They look grown up, huge and bloated, but in cosmic terms, they're still young. They form, live, and die entirely within a narrow slice of time, and then they're gone. Most of the universe's history passes without them. Then you hit the statistical reality, which makes Stephenson 2-18 feel even more like an outlier. If you line up all the stars in the galaxy and sort them by mass, you don't get a flat distribution. You get a steep slope. Most stars are tiny compared to the Sun, red dwarfs with masses between about 1.2 and 0.6 times the Sun's mass. Their radii are a fraction of the Sun's, tens to a few 100,000 kilometers, not millions. They're faint, cool, long-lived, and completely dominate the head count. The Sun is already not typical. It's bigger and brighter than the majority of stars. A star like Stephenson 2-18 sits far out in the tail of that distribution. If you try to draw a simple analogy, say the Sun is a basketball, then most stars in the galaxy are marbles or smaller toys scattered around it. And Stephenson 2-18 is not just a bigger ball, it's a sphere that would fill a chunk of a city block, stretching across streets and buildings. You don't run into many of those. In mass terms, going from a 0.2 solar mass red dwarf to a 40 solar mass giant is like going from a small backpack to a loaded truck. It's not just a scaling up, it's a different regime. So your mental picture of a typical star is doubly biased. First, you're biased because you live next to a sun-like star and that's what you see and feel every day. Second, your eyes and telescopes are biased because the bright, massive stars are easier to see from far away, even though they're rare. So you end up talking a lot about blue giants, red supergiants, and hypergiants, and you almost never think about the ocean of cool red dwarfs and small stars that actually make up most of the galaxy. Once you add Stephenson 2-18 into that picture, the scale stretches so far that the Sun stops looking big. You have one object with a volume on the order of 10 billion suns, pumping out 500,000 times the Sun's energy, on a lifetime shorter than the Sun's by a factor of 1,000, or more, made of the same basic plasma, but arranged in a totally different way. Then you have trillions of tiny, dim, long-lived stars that completely dominate the statistics and never make headlines. So how does your idea of a typical star change after this? It should shift in two directions at the same time. On one side, you accept that the most common star is a small red dwarf that you'd barely notice from a distance, not a sun twin, and definitely not a Stephenson 2-18. On the other side, you accept that the space of possibilities for stars includes objects that blow up your usual scales, stars with radii covering planetary orbits, whose densities drop below any intuitive stuff, and whose lifetimes are so short that they flick on and off compared to the slow drift of cosmic time. Put simply, stars like Stephenson 2-18 sit at the extreme edges of the map. They are rare, unstable, and heavily biased towards already distant, obscured parts of the galaxy, but they tell you where the limits are. Most stars will never look like this, but understanding this extreme case forces you to recalibrate what star even means. After you've internalized a star that big and that fragile, a normal sun-like star feels compact, and most real stars feel very small. And that sets up the final step in this whole story. Once you've dragged your sense of scale through solar system-sized stars, ultra-low densities, near-limit luminosities, and short, violent lifetimes, what are the main things you should actually carry away? What numbers and ideas should stick in your head so that when someone says star, you don't just picture the sun, you picture an entire range with Stephenson 2-18 sitting out at the edge, forcing you to redraw the map. At this point, you've heard a lot of pieces, so let's stack everything on top of each other and see how extreme this really is. Stephenson 2-18 is one star, with a radius of roughly 1.5 billion kilometers, about 930 million miles. That's the distance from the center to the surface. Double that for diameter, and you're at 3 billion kilometers, around 1.9 billion miles. So across, it's basically solar system sized. Take that radius, compare it to the Sun's 700,000 kilometers, and you're talking about more than 2,000 times larger in radius. Cube that factor, and you land in the 10 billion suns volume range. Not 10 suns, not a million, around 10 billion sun volumes. Then look at the power. Luminosity in the ballpark of 440,000 to about 630,000 times the sun, call it roughly 500,000 suns worth of light. and it sits around 6,000 parsecs away, about 20,000 light-years, buried in dust in the direction of the constellation Scutum. Those are the baseline numbers you should keep in your head. Radius about 1.5 billion kilometers, diameter about 3 billion kilometers, volume roughly 10 billion sun volumes, luminosity roughly 500,000 suns, distance around 6,000 parsecs, roughly 20,000 light-years. Any one of those would be impressive. All of them on the same object push it into a different category. So what does that actually teach you about massive star physics? What did this one star force us to confront? First, it makes very clear how different high-mass evolution is from the sun's path. You're looking at a star that probably started with 30 to 50 times the sun's mass, burned through core hydrogen in a few million years instead of 10 billion, switched to shell burning and multiple fusion layers, and ended up as a red supergiant with an atmosphere stretched over solar system scales. Second, it shows you what happens when radiation pressure and gravity are almost perfectly balanced on a knife edge. The luminosity is so high that the outer layers are barely held in place. Surface gravity drops to tiny fractions of Earth's g. Escape velocity at the surface slides down to tens of kilometers per second, and mass loss through winds becomes a built-in feature, not a minor detail. You don't get a calm, stable ball. You get a star that is actively stripping itself down and setting up its own death environment. Third, it pushes directly against empirical limits like the Humphreys-Davidson boundary. If the more extreme distance and extinction values are right, Stephenson 2.18 is operating at or beyond the luminosity where red supergiants are supposed to be unstable and brief. That either means the star is currently in a very short-lived phase we just happen to catch, or our understanding of how long such ultra-luminous red supergiants can exist needs updating. One object doesn't rewrite theory by itself, it forces the models to justify themselves under harder conditions. Now look at the largest star story with that in mind. You've seen how UY Scuti went from around 1,700 solar radii down to about 900 to 1,100 once distances improved. You've seen how VY Canis Majoris and others also shrank when better data came in. Stephenson 2.18's huge radius is built on its assumed distance and extinction in a dusty, crowded region. That means the same thing could happen here. Future infrared astrometry from JWST and extremely large telescopes can nudge the distance down or up, refine the extinction, and move its luminosity and radius accordingly. If the numbers drop, Stephenson 2.18 gets demoted to maybe the biggest to one of a handful of extreme giants. If they hold, it becomes the benchmark example of a star at the absolute upper end of size and luminosity. Either way, the largest star title stays a moving target. It will keep shifting as we do better measurements. We will keep swapping champions in and out of that top slot. So where do you stand in relation to something like this? What is your place next to a 10 billion sun volume? Your planet, Earth, has a radius of about 6,370 kilometers, around 3,995 miles. The sun's radius is around 700,000 kilometers, about 430,000 miles. Stephenson 2.18's radius is around 1.5 billion kilometers. If you shrink the sun to the size of a basketball, about 24 centimeters, roughly 9.5 inches, Earth shrinks to about the size of a small grain of sand a couple of millimeters across, sitting 10 meters away. In that same scaling, Stephenson 2.18 wouldn't just be a bigger ball, it would be something like a sphere large enough to swallow a whole city block, tens of meters, hundreds of feet across, stretching past the buildings, past the streets, turning your entire neighborhood into inside the star. And remember, most real stars in the galaxy are not basketballs in this analogy. They're smaller than marbles, tiny red dwarfs you'd barely notice. Your entire life, all of human history, all of biology on Earth, runs on the energy from a star that is already more massive and luminous than most stars will ever be. Stephenson 2.18 shows you that even that is small in the full space of possibilities. You are dealing with an object that takes that big reference point and scales it up by factors of thousands in size, tens of thousands in luminosity, and still only lasts a few million years before it tears itself apart. So here's the reset you should walk away with. First, star does not mean sun-like. It covers a huge range, from cool red dwarfs that can burn quietly for trillions of years, up through sun-like stars, up to rare monsters like Stephenson 2.18 that burn ferociously and die young. Second, largest star is not a fixed, clean record. It's a snapshot of our current best guesses, with objects like Stephenson 2.18 sitting at the edge, waiting to be confirmed or revised. Third, scale is not your friend here. Your instincts, built on planets and everyday distances, are not set up for a star with a radius of about 1.5 billion kilometers, a diameter of about 3 billion kilometers, a volume around 10 billion times the Sun, a luminosity around 500,000 suns, and a distance of about 6,000 parsecs, roughly 20,000 light years. Any one of those you should keep in your head. Because once you really internalize that one object can be that big, that diffuse, that bright, and that short-lived, you don't look at the night sky the same way. Every point of light becomes a question. Is that a small, long-lived dwarf, a sun-like star, or something out near the edges of the map? And you know now that somewhere in that map, a star like Stephenson 2.18 is quietly saying, your old picture of a normal star was way too small. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.